Good afternoon, Thursday, May 4, 2023. Well, here there's been reading Albert Einstein's out of my later years, and it's really interesting to read these chapters on his interpretations of physics and reality with regards to his theories of relativity, and then the classical theories have been seeing a lot that he lays forward as his desiderata and requirements of future theories, and framed as they usually are in the course of this development of his. That it should be a total theory, that it should be a field theory, that he does have an absolute universe in space-time, if that the principle of relativity is that there's no absolute motion, which we've been talking about as velocity, as meters per second, or seconds per meter of bodies, and that each material point basically is a frame, and about frames and inertial systems. There's some discussion of the Loch Ness monster and what some rest exchange momentum could look like with regards to the open and closed and real interpretations of virtual energy and this kind of thing with regards to the potentials and some potentials and with regards to the space contraction and what is entailed in the results and the developments that make so for that. Then there's ideas of like the stop and go as continuous and this kind of thing. And then another thing that I thought was interesting along these metaphors, that for example for Einstein's train, that there's a teacup on the train so that the rotational kind of builds up its own milieu, and about these things, and about how that connects very directly, of course, to Einstein's separation in his definition after the definitions of special relativity and general relativity, free of otherwise most attachment, and then the connection to his space and time, particularly how he ascribed and basically gave that special relativity is local, and so anything that's non-local is not necessarily so governed by special relativity, and that's okay. These are things that a lot of people don't really take away from a usual introduction to a course and the laws of Einstein in terms of what are the laws of nature according to Einstein, and what they are with regards to physics, which is a study of and a science, and it's a mathematical science, and that there's only really mathematical models, but then they're attached to any kind of physical models via the physical interpretation of behavior of the objects. They're mathematical objects as by the behavior of objects mathematically, this physically, in the causality that thus results. That then this principle of least action is one of the most usual principles in physics, that there's not that much going on outside of these fundamental tendencies and propensities. This restitution and dissipation that are complements and complementary duals. So a lot of talk went into the notions of the complementary duals. And the idea is that for something like a singularity is the idea of a circularity, or that for the classical there's the sum of potentials, and then trying to figure out how to frame that so that whatever ends up becoming kind of a universal frame still is a universal frame and not just vacuous or trivial, but in the end just kind of in the say gradual, that it works out for a gradient and anisotropy, that in the otherwise isotropic medium of the flat space-time, that there's something as simple as why the motion forward in space in time of time brings about that is just reflects a tiny model of contracting framework of what would implement gravity as in accordance with otherwise just a general tendency or propensity over a space, a Euclidean space, the objects within it. That this is the kind of thing that could help, in effect, make for what's in that the models that are these superclassical models have to be accessible to our senses and to brief explanation that unambiguously attaches itself to simple models that are tabletop and open and clear. And that's not always simple, but at the same time, sometimes it is. And it's possible to have something that has some very extenuated effect, kind of like the soap bubbles, and to show slow motion, or to employ something like slow motion photography to help people see something that happens in a very fast regime results in these extra classical effects. So these are the kinds of things that Einstein considers, and more so that he expresses on the constructivist side that it's necessary to attain to them. For then what our models can attain to the superclassical, or as he puts it, the total, and then he wants to be a system driven by continuous transformations, or the differential system, the total differential equation of Einstein's big theory of a formula of everything, and that's the Lagrangian we've discussed, that causality is inviolable, and that time is the time is something that's been established as Einstein's opinion. That otherwise, when we hear opinions otherwise that basically are employing the authority of Einstein as the big hero of physicists of the 20th century, that it's with regards to Einstein that I'm finding it mostly and pretty much agreeable, and that as well I find that what extensions I have to theories of physics, like this rest exchange momentum, and because of the openness of systems after space contraction, or that space contraction is real, or that this light speed rest frame theory makes for that is something simple to get about and around. Otherwise, that light's travel in statics is simple and according to motion. Then with regards to Fresnel and some of these other effects that affect the travel of light. And then there's another bit of theory that still really kind of confounds me, and we might be able to learn some of it from reading this Heisenberg's book on nuclear physics. And what it is about the nuclear transmutation, the fact that elements of chemistry are essentially long-lived. Defined by their atomic number, there are some processes that affect within the nuclear radius of atoms, according to this nuclear physics, transmutation of elements. And then, so I'm trying to figure out that if matter and charge, or mass and charge are basically fundamental quantities that have an exchange, is about the magnetic, in the magnetic fields, it's all kinetic or current based. That it's the stasis of the massy bodies, or the flux or flow of the charged bodies, and those kind of in the middle is complementary duals. And that starts with something like Maxwell's fields and E cross B, and the electric magnetic fields, the classical ones, or the fluid models of electricity, or how much electricity is converted from a hydro dam, and these kinds of interfaces pretty directly and simply and clearly according to gravity, as examples. Then there's for light and radioactivity, to be figuring out how that then matter is kind of in various phases of matter, like solids, liquids, and gases, but matter vis-a-vis massy bodies, but that matter and its nuclear radioactivity and light are one thing, when in the sense that electromagnetic radio frequency energy is a different thing to help relate light and radiation of the thermonuclear processes, because I don't know so much about it. Maybe some of this macroscopic theories of matter and fields will help, explain what's going on with that when there are thermodynamic contributions besides atomic level vibration and gaseous phase reactions according to kinetic and free energy or loose energy, and this processes that are by absorption of light or radiation, or emission of light and radiation as it accompanies these kinds of very slow processes, where the order of half-life of carbon-12 is so slow and regular, or carbon-14 rather, is so slow and regular that it gives rise to the entire notion of carbon dating things by their epochs, tens and hundreds and thousands and tens and hundreds of thousands of years ago. These are the kinds of things that go into a total theory, and then about the pieces that can be put together that say, hey, you're only using in your configuration of energy of experiment, you can feel free to just add these pieces, and what you'll have there is a working model for those pieces. It doesn't much help to have a theory of everything if it's not decomposable for these deconstructivist narratives. So we left Einstein and been talking about the psi function, which is Schrodinger's psi, which is the wave function's probability amplitudes. As we've been talking about in the reading about the path integral and the computation of the probability amplitudes of the propagation equations after the nonlinear electromechanical effects and applications, the propagation equations, and for the scattering theory, the propagation equations, and then for this notions of parallel transport, or what are kinetic laws, classically the propagation equations of what is the propagation of waves. The particle wave duality has the particle model is for discretization and for finite quantities. The wave model is pretty much real and represents surfaces also. That is kind of simple to modify a continuous model a continuous body as a particle and as a wave, but it essentially that is as a wave generally, and then that Einstein is carrying along validating physics, and he talks about the probabilistic interpretation, and as well about what causality would mean, and as well what the non-local would mean, and these kinds of things, that he was familiar with these things, that when he rejected it, it was just to take a side saying, hey, it has to show this and that, not that he was insensate or unawares of the ideas that went into this, basically. Then there's also that he says, basically, that my model of a working physicist needs classical models of things and to have things available to his senses. And so then for an example, he says, nobody will ever be able to see an atom, yet that he ascribes it that it's a real thing, and the various notions of the object sense and it being available to his model physicist. Okay, so there's lots going on, but really it's about this continuum mechanics and what it means to even think of things in the absurdly large and absurdly small, but here mostly the absurdly small, the particles of particle physics. After the elements, which are having atoms, the atomos, the uncuttable, this whole graininess of the smoothness of the continuum, that it becomes a mathematical challenge, and that's where the intuition afforded by the mathematical of an understanding of the smooth and continuous and the graininess and the grit of things and the smoothness and the mix of things, that these become relevant to having an ability to make mental models of this non-standard, which results in super classical, which makes it possible to understand what parts of usual mental models of the way things work, like how water goes downhill, and what would happen if it went uphill. What if it was, that would indicate this opposite of things. It's like what happens when on the ski jump, when somebody changes their potential energy for downward motion, but then according to being accelerated by a smooth gradient, then achieves an upward trajectory and then returns back to downward motion, the ski jump problem. And that's also to frame up how to solve the Laplacian, which is computing the gradient in the partial in any three directions at any one point in a vector field, when really what you're looking for is a principal component that comes over that, defining the maximum, and that kind of stuff, to help get over some of this gimbal lock setups and singularities. And then the other example I thought to bring to mind was the ballet. So ballet is a dance, and basically it is a classical, highly structured, formal sort of performance art. And what is interesting is that there's one aspect of it that basically involves liftoff or flying called ballet. And so the idea of the balaton is basically that you charge up, and then over the course of being able to lift it, people are able to perform either getting lifted excessively high or leaping excessively high. And that this is a real thing. And that is not so much match up according with a given output, but over a range of time, the collection of energy in this rest exchange momentum that adds up to that. And so that's different than something along the lines of, well, here's what you do. You get an array of nanogyroscopes. Now you can input energy to that and get them spinning, and as they spin, they contract in their space. They gain relativistic mass, and so by charging up that system, it basically gains mass. And so in a gravitic field, that would gain mass, and according to this thought experiment, then it would gain weight, and the gravity is field. So it would be weighed more down. So now you have on Earth, and so you spin up this relativistic nanogyroscope array, and then you use a lever to accelerate it going 1 meter per second up. And then you have it let out. So all of a sudden it's much, much, much lighter, relativistically, how it lets this energy out. Maybe it's a light show or something like that. And then it exchanges, its inertia becomes in terms of that lower mass, and it exchanges that inertia for velocity. So does it violate conservation of these quantities? Well, not so much so, although the Earth took a little bounce when it happened. But what happened was you were able to use the mechanical advantage of the lever with a much, much shorter arm and less distant fulcrum that to get it going upwards at a given particular elephant dropped on it or what to send it up at that rate, and then it was just so contrived that the relativistic mass goes to zero effectively, and then but thus its velocity takes off because it maintains its inertia. So I think that's that's one of my thought experiments that I've had for a long time, the relativistic nanogyroscope array, and it's pretty interesting. So back to quantum mechanics, and the quantum mechanics and the classical interpretation is the fact that quantum mechanics affords in such a simple manner statements concerning apparently discontinuous transitions from one total condition to another without actually giving a representation of the specific process. This fact is connected with another, namely the fact that the theory in reality does not operate with a single system but with a totality of systems. He is describing these inertial systems are non-local with respect to each other. Coefficients of C sub R of our first example are really altered very little under the action of the external force. With this interpretation of quantum mechanics, one can understand why this theory can easily account for the fact that weak disturbing forces are able to produce alterations of any magnitude, physical condition of a system. Such disturbing forces produce indeed only correspondingly small alterations of the statistical density on the ensemble of systems, and hence only infinitely weak alterations of the psi functions, the mathematical description of which offers far less difficulty than would be involved in the mathematical representation of finite alterations experienced by part of the single systems. What happens to the single system remains, it is true, entirely unclarified by this mode of consideration. This enigmatic happening is entirely eliminated from the representation by the statistical manner of consideration. It's assuming that the statistical manner is also an enforced randomness. That something effectively makes things, with regards to quantum processes, their statistical behavior as randomized, of where particles land on where the wave would land. That the wave would land everywhere at once with regards to where the particle actually lands on an array of detectors. That this is the kind of thing that is a stronger statement than Einstein has made, but that's implied by what he said. because otherwise it wouldn't, what he said would not be implied by what he said. So he says, but now I ask, is there really any physicist who believes that we shall never get any inside view of these important alterations in the single systems, in their structure and their causal connections? And he said causal. And this regardless of the fact that these single happenings have been brought so close to us thanks to the marvelous inventions of the Wilson chamber and the Geiger counter? To believe this is logically possible without contradiction, but it is so very contrary to my scientific instinct that I cannot forego the search for a more complete conception. And I'm really proud of Einstein for this, because he's saying that, you know, there's a scientific instinct, so this intuition is instinct as well. And then there's, with regards to the Wilson chamber, I think that's a kind of cloud chamber apparatus or something like that. You basically make a cloud of charged particles and you're able to set off sparks in them and stuff like that. And the Geiger counter counts radioactivity of, I'm not quite sure what Geiger counts. That there's alpha particles, beta particles, gamma rays, these kinds of things. I'm not quite sure what it is and how there can be rays if it's supposed to be a particle theory, but there are rays. But now I ask, is there really any that we shall never get any inside view? Einstein is almost asking the question is like, does anybody who not think that according to causality, and that being the only scientific method that we have, is it something would have to have causality to be scientific and admit being a science? That does anybody who thinks that these things are really just arbitrarily non-parameterized, are they really a physicist? Now that's kind of a harsher or less generous reading of what he said, but let's not read it that way. Is there really any physicist who believes that we shall never get any inside view? Yeah, there are physicists who have no reason to believe otherwise. The working theory does not declare them. It's not part of the theory. The working theory is the Copenhagen interpretation, the statistical ensemble and such. And they are not necessarily awares. But I would say any physicist who really believes that that we shall never get inside that, and they might have a very strong belief that we'll never achieve the level of experiment necessary, or we'll never achieve just the simple enough declarations of what would make the field effects so, or never work up the magic ratios that make for a particular kind of diffraction grating, a particular kind of light, that it works out that the functions resulting in various kinds of diffraction don't result in certain particular kinds of caustics under certain particular kinds of focal events, that those are just called noise, but really they have an explanation. There could be some physicists who believe that would never happen, or they might believe that it's all been done or something like that. But by and large, I would say no. So to believe this, he says, to believe this is logically possible without contradiction, but it is so very contrary to my scientific instinct that I cannot forego the search for a more complete conception. So Einstein thinks the wave function is real, and he would have to have some kind of extra classical model to define how it could be so. To these considerations, we should add those of another kind, which also voice their plea against the idea that the methods introduced by quantum mechanics are likely to give a useful basis for the whole of physics, and that Schrödinger equation, absolute time, and also the potential energy play a decisive role, while these two concepts have been recognized by the theory of relativity as inadmissible in principle. I don't know about that. I mean, we're talking about the time, and that then when we have relative motion, you know, and so this is he's expressing at this point. This is the first time I've really seen something, when I've been reading this, where I'd have to read it, is that it's something where he's saying, I'm standing by my theory of relativity in this matter, and some particular interpretations that might so follow it, when otherwise throughout he's been developing and cultivating for his total field theory some more. So this is where he's like, I don't have a total field theory that I can show you. So at this point in time, and as far as I'm reading from here, he goes back to his kind of earlier stated views, and so he's like, forget chapter 12, forget chapter 11, and go back to chapter 10, and imagine if you started here as a conscientious model physicist of a model physicist, abstractly. And so I can only read that as so here instead of just being vacillating or waffling, because I think he's a grandiose hedge, and so far that's kind of my theory, is as an object as a grandiose hedge, he can only behave as a grandiose hedge. So he's setting us up. Give a useful basis for the whole of physics. In the Schrodinger equation, absolute time and also the potential energy, as would be in a theory of some potentials parameterized by time, play a decisive role, while these two concepts have been recognized by the theory of relativity as inadmissible in principle, or secondary, or nonlinear, or asymptotic. If one wishes to escape from this difficulty, he must found the theory upon field and field laws instead of upon forces of interaction. Field theories in their field laws basically emit forces on their field. It's a vector field. Field theory is a force theory. All forces these days in the field theories are called, all the forces are in fields. So that's so for quantum mechanics and particle physics writ large. And then with regards to forces in the bodies, well, then we have the Riemannian matrix attached to the central bodies. So when we have a sparse system, like a solar system, it's got a sun and 9 planets and myriad asteroids, too small to count. Those have central symmetries about those, whereas in uniform and continuous fields, the forces are in the fields. And so about his forces in fields, he's talking about in terms of the space contraction, his theory can be built with all the stuff included that Einstein has in his desideratum and requirements of theory about making those distinctions. It's kind of like when you think about distribution of things, oftentimes you'll find for a billion different things that most of them are one or several kinds of things. You call these the principal components. And then you have all these probables, majors, minors, and the long tail. So for kinds of things and categories, the usual enough distribution of them is principal components, or the mode and principal components, majors, minors, and long tail. So when you have something like a solar system with planets and a sun, planets, moons, asteroids, and dust, comets and dust, then the idea is that each of the systems that are significant to have their own central symmetries and their own frames, admit to the analysis being like that and having their own Riemannian metrics. But otherwise, it's still one force and one field theory everywhere, with the pieces stitched together like so. And so let's go back to Einstein and pick up where he left off. If one wishes to escape from this difficulty, he must found the theory upon field and field laws instead of upon forces of interaction. This leads us to transpose the statistical methods of quantum mechanics to fields, where these are Einstein's fields. That is, to systems of infinitely many degrees of freedom. Arbitrarily many degrees of freedom. It depends. It's relative. Although the attempts so far made are restricted to linear equations, which, as we know from the results of the general theory of relativity, are insufficient, the complications met up to now by the very ingenious attempts are already terrifying. The complications. It certainly will rise sky high if one wishes to obey the requirements of the general theory of relativity, the justification of which in principle nobody doubts. Well, here the idea is to help implement general relativity with this space contraction. So figuring out how to kind of re-implement the transition from a Riemannian metric of curvature. It's about the rotational. It's really about the rotational space. And about how to figure out those singularities is a theory of vortices, kind of, and we can point back to that to Descartes. We can point back to that, before the theory of fundamental substances as vortices or spirals or rotational and waves. It's been around forever. The justification of which in principle nobody doubts. To be sure, it has been pointed out that the introduction of a space-time continuum may be considered as contrary to nature in view of the molecular structure of everything, which happens on a small scale. No, these are what I reject finite discretism or retro-finitism as wrong. If it's continuous space-time, it's continuous space-time. Mathematics continuum is most certainly smooth and continuous, and not granular, digital, or otherwise not continuous. And but he is expressing that for some people it's like they want a smallest brick, and it all fits everywhere. But it goes back to this idea: if you add the Planck length, that Planck length is the smallest length that involves observables. Smaller than an atom, it's the smallest length that involves observables. But if you put those squared to each other, took the diagonal, it would be an irrational number of those. Minus 1 is like 1 minus root 2 of those. That would be an irrational number of those, which would be less. So there'd be either no straight lines or no right angles, in the sense that it has to be that discontinuous. And then that there are geometric mutations in the continuum mechanics in collapse to the original in the small. It is maintained that perhaps the success of the Heisenberg method points to a purely algebraical method of description of nature, that is, to the elimination of continuous functions from physics. Then, however, we must also give up by principle the space-time continuum. It is not unimaginable that human ingenuity will someday find methods that will make it possible to proceed along such a path. At the present time, however, such a program looks like an attempt to breathe in empty space. This is Einstein's usual put down. There is no doubt that quantum mechanics has seized hold of a beautiful element of truth, and that it will be a test stone for any future theoretical basis, and that it must be deducible as a limited case from that basis, just as electrostasis is deducible from Maxwell equations, electromagnetic field, or as thermodynamics is deducible in classical mechanics. However, I do not believe that quantum mechanics will be the starting point in the search for this basis for classical motion. Just as vice versa, one cannot go from thermodynamics, respectively statistical mechanics, to the foundations of mechanics. It could be. It would be cumbersome, but the idea is to make it so that it's self-similar to all regimes or something like that. That the same kind of model adds it all up. In view of this situation, it seems to be entirely justifiable seriously to consider the question as to whether the basis of field physics cannot by any means be put into harmony with the facts of the quantum theory. Not if there's just one theory, but he's defending people who, for example, like himself, may had put a wall between them before. And it seems he doesn't unfairly and wrongly overgeneralize. Is this not the only basis which, consistently with today's possibility of mathematical expression? He's also expressing that mathematics owes physics better mathematical models. Mathematics is simply unequipped to model some of these superclassical models. The belief prevailing among the physicists of today that such an attempt would be hopeless may have its root in the unjustifiable idea that such a theory should lead, as the first approximation to the equations of classical mechanics for the motion of corpuscles, or at least to total differential equations. As a matter of fact, up to now, we have never succeeded in representing corpuscles theoretically by fields free of singularities, and we can a priori say nothing about the behavior of such entities. One thing, however, is certain. And he emphasizes one thing, however, is certain. If a field theory results in a representation of corpuscles free of singularities, then the behavior of these corpuscles with time is determined solely by the differential equations of the field. This is kind of moot. The next section is relativity theory and corpuscles. Let's see, and he talks about Schwarzschild radius, which is the radius so small that if matter is all within it, then it's so dense that it becomes a black hole. Which is simply by manipulation of the formula of gravity. About singularities, and then he ends with a summary. So what I figured to do is kind of look at that next time, and as that will then get into the next chapter, if we get to the summary next time, then the next chapter is the fundamentals of theoretical physics, and he talks about Lorentz and Planck and Niels Bohr, de Broglie and Schrödinger, and G, the configuration space. He mentions Gamow, about radioactive disintegration. Lessings finds saying that the search for truth is more precious than its possession. Then there's another chapter called The Common Language of Science, and another chapter called The Laws of Science and the Laws of Ethics. An elementary derivation of the equivalence of mass and energy follows. That there's more reading to come from Einstein's book. Now I want to look at this nuclear physics for a moment and just kind of get a sense of what Heisenberg sounds like. Rutherford's atom model, the periodic system of elements. The present English edition, appearing sometime after the German one, may be of interest in connection with the history and principles of nuclear physics rather than with respect to its recent development. General properties of the nuclear field. The nuclear forces as exchange forces, the saturation of nuclear forces. The stability of nuclei, nuclear reactions, the tools of nuclear physics, the practical application of nuclear physics. Chemistry, biology, biochemistry, medicine, printed in Nature. Nuclear physics is one of the most recently developed branches of physics. There's alchemy. It was one of the traditional science. It was science of the day. It was pseudoscience, or not necessarily advised by the scientific philosophy of today, the scientific method. You know. But alchemy, the idea was to turn lead, a common metal, a base metal, an inexpensive and cheap metal, into gold, a rare metal and a valuable metal. If you could turn lead into gold, the argument goes, you could upend the gold market by flooding it with lead. Well, some say the better course is that somewhere in space there's an asteroid and it's made out of gold. So you go find that and bring it back to Earth, and it would be like more gold than the Earth ever had before, and it flood the market with an asteroid from space of gold. But anyway, and so that's kind of the first study of nuclear matter, because metals transmute to each other, and under sufficient and proper conditions, yes, you can make gold from lead. It involves irradiating it and resulting out that nuclear transmutations occur that make it. It would make a very highly toxic and radioactive hunk of radioactive transmutating gold. It would be gold, at least in some small part. The nuclear chemistry and nuclear physics and that is kind of if electricity is bad enough, it's invisible, but it can shock you. Is that nuclear physics is kind of like it's invisible, and you won't even know that it shocked you. Modern atomic theory up to the end of the 19th century. We think of Madame Curie and the Curies. These is this husband and wife pair of French physicists who studied, chemists who studied radioactive materials, and then there's the discovery of the X-ray in Roentgen and this kind of thing. The X-ray was a great thing. It's like light, but it goes through solids. It's X-ray. It's like, but it's heavy. It can be very heavy. The phlogiston, Lavoisier, chemicals, and so this is just kind of the discovery of the stoichiometric in chemistry. I'm reading it. I'm just kind of scanning. Prout actually spoke against the theory of absolute indivisibility of atoms. The fact is the basis of his view that all atoms were built up of hydrogen atoms. It's a hypothesis. A new era in atomic theory was introduced by Faraday, which combined atomic theory with the theory of electricity. Faraday discovered that the masses of the substances transformed by a certain definite quantity of electricity are related to the so-called equivalent weights, and thus in the simplest cases, these of univalent substances, to the atomic weights of the substances concerned. This discovery indicated that electricity too possessed an atomic structure of such nature that each atom or each molecule of a chemical compound is always associated with one or more atoms of electricity, even though in some manner then still unknown. This is pointed out by Weber as early as 1848. Maxwell, Boltzmann, Clausius, Loschmidt. Free atoms of electricity, atoms not bound in atoms of ordinary matter, were discovered by Hittorf in cathode rays, which are a consequence of electrical discharges in highly attenuated gases. Yeah, a lot of what happens in light and the transitions could be essentially considered a nuclear process vis-a-vis an emission process. All right. Well, that's something to follow up in a later time. I hope that was an interesting brief pause while I looked at this for a second, kind of thought about it. Yeah, I got this book, that book, the other. Been reading them for this time, and reading for Einstein still, it was about as much as I have to take away from it so far as the rotational singularities and rotational frames, mass energy equivalence, and then the cosmological constant for that is like space-time is flat, but there's always a cosmological constant for any nonlinear or running constant or asymptotic part there, and that otherwise I can take pretty much, I feel comfortable accepting Einstein's theories for general relativity as modeling these central symmetries as about a Riemannian curvature, as about otherwise that's just a model of a bounds of a certain regime or a region about some orbits with respect to orbiting bodies when a smaller body orbits a larger body, general relativity, and that general relativity for the kinetic has this rotational mass energy equivalence. And then for special relativity, I can accept what he's got going with the local part of that after the otherwise that, and that each one has its own little space, but really just reflects that then it just propagates freely and is not so carried by the frame. But in statics, light would go along yet, but light is governed by this. And that light is governed by the geodesy as well. I'm still kind of wondering about that, because then I'd be wondering about some of this double vision type stuff, and I'm interested in the Fresnel approaches to lensing when it's possible that some light of a particular frequency wavelength could be distorted or focused by passage around an object, besides as usually there would look like the same mechanism as gravitational lensing, but that it just kind of follows out this flow while it follows the same track. And then under what conditions it wouldn't. And then the idea to validate something like that would be to make it so, and to establish for some, basically inside of something as rough as like the inside of a geode, you know, about 1/8 or 1/16 of an inch, or something that's uniform at that grain, like a long tunnel of that with something that emits a particular form of light, and then showing what happens when you shoot something up in a circle around that. For example, it's spun around on a rope fast enough or something, or is on the edge of a large flywheel disc. So basically you just use the whole disc to spin it around and just have something on the edge. Then the idea would be to figure out a tabletop experiment to show those kinds of things, and that it would be possible to implement, you know, without $1 billion accelerator, still something along those lines. And it should even be simpler. I mean, if we figure out something that basically just in accordance with the matters of reflection of some formulas, that's the idea, is to figure out how to make tabletop apparatus that can help show that these ideas of fault gravity and these extensions past Einstein's theories of relativity, and implementing Einstein's total field theory, because Einstein's total field theory is an ideal thing. That my theory of some potentials, or theory of sigma or theory of omega potentials, Einstein is going to point at that and say, yep, just what I said. It's a total field theory. It's got a continuous space-time. It implements relativity and general relativity, or thank you, I can trace that out for myself from this here, and on we'll go. All right, well, on we go. Hey, have a great day. So long.